Hello everyone. So far in projectile motion, we've kind of looked at one-dimensional cases, whether that's the straight down free fall or the up and down 1D projectile motion. So now we're going to try to take this into two-dimensional projectile motion. Now remember that a projectile is something for which we can consider only gravity as acting. Right? Only gravity acts upon it. We can neglect air resistance and any other effects. So the question becomes, well, how are we going to deal with a two-dimensional projectile? And we're going to take a tact that we've actually taken in other situations, whether it be things like motion or forces, especially when we've had two dimensions. I'm going to do a couple of demos or show you a couple of movies of demos. These are demos that I will do in class so that they can see them, but if you're just watching the movie here. First one is the ballistic cart. You might remember the ballistic cart. We used it earlier on in the year as an example of inertia. It's a little cart that has a spring-loaded projector on it. You put a ball in it when there's a little photo gate on the side, and when it gets triggered, right, it shoots the ball straight up, and it comes straight back down again. Then the question is, well, what happens if we give it a little push so that it's moving constantly to the side, so that it now has a horizontal motion to it? Right? What happens to the motion of the ball? Does it do anything different? Does it land behind it, in front of it? Right? Where does the ball land? So let's watch a little video here of this ballistic cart. So there's the straight up and down. Now he gives it a push. Right? And the ball travels in a full parabola, up and down and left to right. There's a faster one. You can see it moving. Right? But notice how it basically keeps up with the cart. Right? Now, we used this as an example of inertia, that once the ball was moving horizontally, it stayed moving horizontally, even after the cart was no longer acting on it. Right? But this is also can lead us to a way to analyze this motion, because notice it didn't matter whether the cart was moving horizontally or not. It didn't matter whether it was moving fast horizontally or slow horizontally or not at all horizontally. The ball did the same motion vertically. It went up just as high. It came down, right, just as much. It took the same amount of time up and down. In other words, the horizontal and vertical parts of the motion could be pulled apart because they're independent of one another, right? And we can analyze them separately. And that ballistic cart kind of shows that. It didn't matter if it was moving horizontally or not. The vertical motion was the same anyway. So that would allow us to take a two-dimensional projectile motion and split it up into two parts, horizontal and vertical, and look at those separately. Well, here's a second device. It's a classic physics device. And this guy's going to come out, he's going to build it, and then he's going to show it to you. But the device basically, here, let me get it started here, starring Alan, some physics professor, I guess. So he's going to come in and set this device up. And this device does two things. There'll be a ball on either side of it. The ball on, I believe, the left side gets dropped, and the ball on the right side gets shot off horizontally. All right, from the exact same height at the exact same instant of time. And the question is, which ball hits the ground first? The one that's dropped, right, or the one that's shot off? So here's the one on the left-hand side. See how the ball just sits on this? So when he triggers it, the ball is just dropped. But on the other side, he's going to put a ball here, and now it's going to get hit, and that shoots the ball horizontally. So when he sets both, which ball hits the ground first? Ready for this? Here we go. So there's the one that's going to get dropped, and there's the one that's going to get shot horizontally. Let's watch that part again. So pretty clearly, right, the ball that was dropped and the ball that was shot horizontally landed at the ground at the same time. The fact that the blue ball was also moving horizontally didn't affect what it was doing vertically. And I've kind of done this in a motion mappy kind of way, because it's kind of classically how we used to look at it. This is a picture I took out of one of our textbooks. And you can see here that the ball, which is kind of, again, like a motion map, it's equal intervals of time. And at any interval of time you pick, the two balls are basically at the same height, even though one's moving horizontally and vertically, and one's only moving vertically. Right? So the fact that the yellow ball has a horizontal motion to it doesn't really affect what it does vertically. Right? And anytime it's at the same height, and they reach the ground at the same time. Now, from a little more mathematical or physics standpoint, it's because let's think about what's happening vertically. Okay? For both balls vertically. First off, what's the initial vertical velocity for both balls? Well, for the dropped ball, I think that's fairly obvious. It starts from rest. It's just dropped. So its initial vertical velocity is 0. But what about the shot ball? Well, in the case of this picture or the video you saw, it was shot horizontally to start out with. Shot horizontally. Well, how much of horizontal is vertical? None. Right? So if it's shot horizontally, the initial vertical velocity is 0. Now, if it's shot at an angle, then it has an initial vertical velocity. But then it wouldn't do what we're seeing here in the diagrams, right, and what we saw in the demo. So we're going to spend a day or two here and actually even do a lab in class or a practicum in class where we're going to be shooting things horizontally. Right? And one of the key things to pick up there is that means it has no initial vertical velocity. Now, in terms of vertical displacement, both balls have the same distance to fall vertically. Right? They start at the same height. Sure, this one goes further because it goes horizontal, but we're talking about vertical. And then what forces act on them after, right, they're released? Not while they're getting hit or whatever or dropped, but after they get released, the only force acting is gravity. And when gravity is the only force acting, we know that the resulting acceleration is negative 9.8 meters per second squared if we're near the surface of the Earth. So if both balls have the same initial vertical velocity, 0, they have the same vertical displacement to fall, and they have the same acceleration, well, yeah, they're going to take the same amount of time. And I know it sounds like it, but it's not magic, right? Physics. But that's only true if we can neglect the fact that the one ball also moved horizontal. So this demo is again to show you the same as the ballistic pendulum, that it doesn't matter what one ball is doing horizontally to determine what it's going to do vertically. Right? Horizontal and vertical, things that are perpendicular to one another, are independent. And therefore, we can pull the motion apart into two parts, horizontal and vertical, and look at those separately. Isn't that what we've done all year long for things like, say, forces? If we had a force acting on an angle, we don't deal with that force acting at an angle. We break that force up into perpendicular components, horizontal and vertical. And then we look at, well, what's happening with the horizontal forces and what does that tell us about the motion? And what's happening with the vertical forces and what does that tell us about the motion? So we've always kind of split two-dimensional problems into two one-dimensional perpendicular problems. And we're going to continue to do that with two-dimensional projectile motion. So we're going to analyze a little lab here, and it's another Pivot Interactive, a really good one, and very clever. So let me show you a little bit of what the Pivot Interactive looks like here. So let's break down what's happening, okay? There's 3 different views of a single throw of a ball, okay? The main view, which is this one right here, they call it side view. That's just the view of what the ball's doing, right? And notice it's going up and down and left to right. So it's got the full parabola, full parabolic motion of a two-dimensional projectile. this is the super clever part. In this top frame, which they call top view, they flew a drone above it, straight directly above it, with a camera. And they filmed it from the top view. And watch what the ball looks like from the top view. Doesn't it look like it's just going left to right, like it's one-dimensional? Right? You don't really see the up and down motion from the top view. So we're going to use the top view to isolate the horizontal position of the ball as a function of time. You'll be able to come up here and turn a ruler on, and a horizontal ruler, and you'll come up here and turn a stopwatch on. Right? You'll zero the stopwatch when the ball just leaves her hands. That's part of the setup to the pivot. It's inside the pivot and explains how to do that, right? Like as we've done in other pivots in this unit. And then you're going to measure how far the ball moves as a function of time horizontally. But then check out this view. This is from the end. They call this a front view, and watch the ball. So do you see how this one isolates the up and down motion? You're looking at it from the end. Yeah, in reality, it's going up and down and right and left. Right? But if we then turn, we put a vertical ruler here. Okay, we're going to put the 0 at the ground level here just so that we have a nice solid reference point to use. We can measure where the ball is on its way up and on its way down. Right? So the front view over here in the corner is going to be the vertical position versus time. So we're not going to actually use the side view other than to tell us kind of, well, what is the ball actually doing? That it's a two-dimensional projectile. I thought this was a real clever way to do this. It's really hard to do this without some sort of really high-tech movie analysis software. Okay, so I thought this was a good way to do this. So again, all the instructions are inside of the pivot and on your lab sheet. Okay, and you're going to see that the motion of a projectile horizontally and the motion of a projectile vertically, when it's in two-dimensional projectile motion, are familiar models that we already know a lot about and therefore can apply and fully describe the motion of a two-dimensional projectile.